Section 7.4, how to prove identity, trigonometric identities, or how to verify identities. Identities are basically something, the reason called identities because something is identical to something else. So we need to prove they both are the same. What are the strategies in proving something equals something else? So if I want to prove, if I want to prove A equals B, the strategy here, the first thing is we take A and try to get to B. So B, think about B as the answer in the back of the book. So you take A and get to B, or you start with the right hand side and get to the left hand side somehow. But try not to work on both sides, unless if you're going to do some work on the scratch paper. So what are some of the things we can use? As good thing to do, always go from the large side to the smaller one, because in this case you will have more options to work with. If you can factor, do so. Use factoring. If you can expand, that would be another thing to do. If we have fractions, try to combine fractions. In some rare cases, we rationalize. And if you stuck on the entire problem and none of these work, convert into sine and cosine. So whatever side you're working with, you change it into sine and cosine. It will make it much easier for you to work with. Now, before we start looking at some examples, we need to recall basic identities we covered in the previous sections. Some of those identities, like tangent alpha, very important. It's sine alpha over cosine alpha. Cotan alpha is cosine alpha over sine alpha. We have the most important identity, sine square alpha plus cosine square alpha is 1. And remember, from this you can get two more identities. You can get sine squared is 1 minus cosine, or cosine squared 1 minus sine squared. We have 1 plus tangent square is secant square, or 1 plus cotan square is cosecant square. We of course need to know the odd even identities like sine negative alpha, cosine negative alpha, those ones. Make sure you review them as well. Also, we need to recall the algebraic expansion formulas, the a plus b squared and a minus b squared. This is not a squared plus b squared. It's a squared plus 2ab plus b squared. And this is a squared minus 2ab plus b squared. Also, a minus b times a plus b, it's a square minus b square. It helps. All these help. We're going to put all this together to help us prove identities. Let's start looking at an example. Let's look at this one. Sine x over cosecant x plus cosine x over secant x equals 1. So how do we start proving such an identity? So look at the larger side. It's the left side. We got a lot of options to deal with on the left side comparing to the right side. The right side, there's nothing can be done almost. Here we have fractions we can combine. But before we combine them, the common denominator might be difficult to find here for these two. So what do we do instead? We can rewrite or change this or convert into sine and cosine. So cosecant is 1 over sine, and secant is 1 over cosine. And this would equal to, remember, this is over 1. This is the division sign. So sine x over 1. We switch the division to multiplication and flip the lower fraction. Flip this fraction. Plus, Keep the cosine x over 1 the same. Switch division to multiplication and flip the fraction. So that's cosine x over 1. So what do we get in return? This is sine square x plus cosine square x. Oh, what is this? This is 1. And that gives me what I need. I needed to prove that this is 1. More examples. The more examples we cover, the better for you. So that's example 2. I'm going to call this is example 1. 1 plus cosine alpha, tangent alpha, cosecant alpha over cosecant alpha equals 2 sine alpha. So how do you do this? I'm going to start with the left side. Most of the time, the first thing I will do is write down the side I want to work with. I can't expand, I can't factor, I can't combine fractions. And so look at the answer, it has only sine in it. So I keep an eye on the answer. So what I'm going to do is I'm going to convert everything I come across. Like cosine, I can't do anything, but tangent is sine over cosine. So sine alpha over cosine alpha. Cosecant is 1 over sine alpha. And cosecant again 1 over sine alpha. So let's see what we get. 1 plus cosine alpha cancels and sine alpha cancels. So the whole thing simplifies simply down to 1 over sine. 1 plus 1 is 2. So 2 over 1 over sine. And this is again the division sign. So what do we do is 2 over 1. We switch division to multiplication and flip the fraction. Sine alpha over 1. So that gives us what we need. Another example. 1 over cosecant x minus 1 minus 1 over cosecant x plus 1 equals 2 tangent square x. So it would be more convenient to start on the left hand side. So for the left hand side, we can combine the fractions, right? So the left hand side, we can combine the fractions. The common denominator is cosecant x minus 1, cosecant x plus 1. And what goes on the top? So here we get cosecant x plus 1 minus, this minus sign is very important. So we put a parentheses there. And here we have cosecant x minus 1. So on the top we get cosecant x plus 1 minus cosecant x plus 1. What can we do in the denominator? That's cosecant x square minus 1 square. So I used a minus b, a plus b. It's a square minus b square. These cancel each other. So I got 2 on the top. 2 on the top. The denominator is just, the answer, is tangent square. So what are we going to do with this? This is cosecant square x minus 1. We recalled today in this section, we have something that connects or have cosecant square. So from here, cotangent square alpha, if you subtract 1 on both sides, is cosecant square alpha minus 1. So let's see, cosecant square alpha minus 1. Cosecant square alpha minus... Oh, that's the one here I can get. Cotangent square alpha, x in this case. And we know, so this is 1. 1 over cotangent is tangent. So it's 1 over 2 times tangent square x. And that's what I wanted to prove. Let's look at more examples on this, but slightly different. Let's call this is example 4. Cosecant to the 4th alpha minus cosecant square alpha equals cotan to the 4th alpha cotan square alpha. So that's example 4. Let's see how to do this. There's many ways, of course, to prove each identity. Different people might approach differently. To start with this one, Keep in mind, this is all about cosecant and cotan, and I just use this identity here that connects these two together. Let me write it down here. That cotangent square alpha plus 1 is cosecant square alpha. Okay, so maybe we might need that. So this here I see to the 4th power. Maybe if I factor out cosecant square alpha, that'll leave cosecant square alpha minus 1. Cosecant square alpha minus 1. Okay, so I need this to be in terms of cotangent. So from the box thing there, I can replace this with cotangent square alpha plus 1. And this one here inside the bracket, cosecant, from this boxed formula, cosecant square minus 1 is cotangent square alpha. If we distribute now, multiply this by this and this by this, we get cotangent to the 4th alpha plus cotan square alpha. And that's what we wanted. So in that example, we use both factoring and expanding. What about if they ask us to prove tangent opposite value of natural log of opposite value of tangent theta to equal opposite value of sine theta minus natural log of opposite value of cosine theta? How do you prove this? Well, we start with the left-hand side. Let me rewrite it first. Tangent is sine over cosine. So cosine theta over sine theta. And we know that one of the properties of natural log, if you have u over v, is natural log of u minus natural log of v. So we can use this here. Natural log of the top minus natural log of the bottom. And that proves it. Not that difficult. Another example, cosecant alpha minus cotan alpha square equals 1 minus cosine alpha over 1 plus cosine alpha. Let's start with the left-hand side. So cosecant alpha minus cotan alpha all squared. How do we do this? Look at the answer on the right side. It's only cosine. So it would be convenient if you write this as 1 over sine, and this is cosine over sine, all square. And before I square this, notice that they have a common denominator sine alpha. So on the top we got 1 minus cosine alpha all square. Keep an eye on the answer. It's only 1 minus cosine, 1 plus cosine. So it's all of it has just cosines in it. So if I want to square this, I'm going to do the squaring of the top over squaring of the bottom one, like so. I'm not going to expand because if you look on the answer, I need 1 minus cosine. So from here, I can write the top as 1 minus cosine alpha times 1 minus cosine alpha. The denominator sine square, how do I convert cosine square into sine or sine to cosine? It's 1 minus cosine square alpha. Let's keep the top the same because I do need one of the factors to stay there. The denominator looks like a square minus b square because that looks like that. It's a minus b, a plus b. And that allows me to simplify these two. And that gives us 1 minus cosine alpha over 1 plus cosine alpha. That's what we need. That's basically what this section is about. Let me add one more example. Let's say we are asked to prove sine x minus cosine x square plus sine x plus cosine x square equals 2. This is just an example about expanding. You know, if you look on the left-hand side, definitely we need to start with the left-hand side. And in this left-hand side, this looks like an A and this looks like B, A minus B square. A lot of students, they think it's A square minus B square. It's not. It's a squared minus 2ab plus b squared. That's the first one. Plus, so this plus sign here. Again, this is a and b. A squared plus 2ab plus b squared. Notice how this and this cancel. Sine squared plus cosine squared is 1. Sine squared plus cosine squared is another 1. So the answer is 2. The answer is 2. The more you practice, the more this becomes more and more fun. So make sure you do these examples first before you attempt the homework problems. It's very important. And of course, all these identities or any identity you're going to come across, you do need to know the basic rules, the basic formulas, like these ones on this page. Those are very important.